In this video, I'm going to show you how to find the general solution to a first-order separable ordinary differential equation. So here we want to find the general solution to this differential equation right here. And the general solution is just the function y which satisfies this differential equation. It's the function whose derivative is equal to the function itself squared times e to the x, where x is the input to the function y. So one thing that we can do to make this problem a little bit more intuitive is to replace this y prime with an equivalent representation of the derivative. Let's replace it with dy over dx. So dy over dx equals y squared e to the x. Now the reason why this makes the problem more intuitive is because now we have a dy and a dx that we can treat like terms in the equation. If we can move all of the y terms to one side of the equation with the dy and all of the x terms to another side of the equation with the dx, then we can just integrate both sides and that'll get rid of the dy and dx, and we'll just have an equation relating x and y, and then we can just solve for y in that equation. So that's the high-level plan for solving this differential equation, and now let's actually execute that plan here. So first step is to separate the differential equation. Let's get all the y on one side and all the x on the other side, including the dy and the dx terms. The dy should go with the y's and the dx should go with the x's. So let's first write down what we have. We have that dy over dx equals y squared e to the x. And we can start off, this is a fraction, dy dx, we can start off by canceling out this fraction by multiplying both sides by dx. So let's multiply by dx, and then we just have a dy on this side, and then we have y squared e to the x dx. Okay, so now we just need to move this y squared to the other side with the dy, and that's pretty straightforward. We can just multiply both sides by 1 over y squared. So the left side becomes 1 over y squared dy, and the right side just becomes e to the x dx. Now that we're done separating the equation, we can actually integrate both sides to cancel out the dy and the dx terms. So let's write it down over in this column in the integration step. We'll just write down what we have to start with. 1 over y squared dy equals e to the x dx, and let's just apply an integral to both sides. So now just solving these integrals, integral of 1 over y squared dy, well that's just negative 1 over y, and then plus a constant, plus constant 1. And then the integral of e to the x, well that's just e to the x itself, plus another constant, c2. Now we've got an equation relating y and x, and we can solve that equation to find the solution. We just want to solve for y here. So let's write down our equation. Negative 1 over y plus c1 equals e to the x plus c2. And our first step, let's just simplify this a little bit. Let's move the constants to the same side. So let's subtract constant 1 from both sides. So negative 1 over y equals e to the x plus c2 minus c1. And c2 minus c1, we can just call this another constant, because a constant minus constant is just constant. So let's call that c3. So now we've got a bit of a simpler equation, just negative 1 over y equals e to the x plus c3. And we can solve for y here. So first of all, let's just flip both sides of the equations. We'll treat them both as fractions, and then take the reciprocals of both sides. So we'll just get negative y over 1, or just negative y, equals 1 over e to the x plus c3. And then we can just cancel out that negative by multiplying both sides by negative 1. So y equals negative 1 over e to the x plus our constant. As a reminder, it's very important to include the constant and carry it through our computations here to find the solution, because different values of the constant correspond to different solutions of the differential equation. Whatever value we plug in for the constant, the resulting function is a solution to the differential equation. But in order to consider all the solutions to the differential equation, we allow the constant to remain arbitrary. So now that we know the general process for solving a first-order separable ordinary differential equation, let's try it on a tougher one. This one's going to require a bit of work in the separation and integration and solution phases. But first of all, let's go ahead and replace that y prime with dy over dx, just so that we can begin our separation. So 3 dy over dx times y squared e to the negative x minus x secant y cubed equals secant y cubed. Okay, so we want to get all the y's on one side and all the x's on the other side. So one thing, last time we multiplied by dx right off the bat, but why don't we try to group up some terms first? Like here we see there's a secant and a secant. Let's try to group up those secants just to simplify the equation a bit. So we'll add x secant y cubed to both sides, and we'll get 3 times dy over dx y squared e to the negative x is equal to secant of y cubed plus x secant of y cubed. And now we can go ahead and factor out a secant y cubed from these two terms. So 3 dy over dx y squared e to the negative x equals, that's 1 plus x times secant y cubed. Great, so this equation is a little bit simpler because now we're just multiplying terms on each side rather than having a subtraction here. And we can go ahead and multiply by dx to get that out of the fraction. So just 3 dy y squared e to the negative x is equal to 1 plus x secant of y cubed dx. And now we want to get x and y on their own sides. So let's start off by trying to get all of the y's on this side. So we'll move that e to the negative x to the other side. We'll multiply both sides by e to the positive x. And the result from that, let's also rearrange the side a bit. Let's put 3y squared dy. And then the e to the negative x goes away because we're multiplying by e to the positive x. And then the result of that is just 1 plus x secant y cubed e to the positive x dx. Now we're almost there. There's just the secant y cubed that's on the side where all the x terms should be. So let's get that term over to the left-hand side where all the y's are. So we'll just divide both sides by secant, and we'll get 3y squared times 1 over secant y cubed dy is equal to 1 plus x e to the x dx. And we can simplify this a bit. 1 over secant is just cosine. So this is really just 3y squared cosine of y cubed dy equals 1 plus x e to the x dx. So now we're good to go ahead and integrate both sides. We've got an integral of a function of y with respect to y and an integral of a function of x with respect to x. And we can go ahead and proceed with our integration. So on the left-hand side, our integral of y, this is going to be a U-Substitution integral because we see a y cubed here, and there's also its derivative, 3y squared over here. So let's let u equal y cubed, and then we get du equals 3y squared dy. And so now we can replace some terms in this integral. This just becomes, well, the cos y to the third becomes cos of u, and then the 3y squared dy, well, that's just du. So this is just integral of cos u du. and we can go ahead and compute that integral. Why don't we just do that? So integral of cos is just sine. So sine u. And then we'll just substitute in for u to put it back in terms of y. So that's just sine of y cubed. So sine y cubed. Alright, so now to tackle the other integral. And the other integral is going to be a little bit more tricky. This one is going to require integration by parts. So remember our formula for integration by parts? We'll just write it up here. Integral of u v prime dx is equal to u times v minus integral of v u prime dx. So what should we choose as u? Well, we want u to become simpler when we differentiate it. So which one of these terms becomes simpler when we differentiate? E to the x just stays the same, but 1 plus x will become a lot simpler when we differentiate that. The 1 will go away, the x will just turn into a 1. So let's set 1 plus x equals u. So u equals 1 plus x, and then that means u prime is the derivative, so the 1 goes away. Derivative of x is just 1, so u prime equals 1. And then that makes up our choice of v prime. That's just the other term, e to the x. So v prime equals e to the x. And then v is just the antiderivative of that. So v is just antiderivative of e to the x, which is just e to the x again. Alright, so now we can re-express this integral as the right-hand side here, u times v, so 1 plus x times v is e to the x, minus the integral of v times u prime, v is e to the x, and u prime is just 1, so times 1 dx, and great, now this is some integral that we can actually solve. Integral of e to the x, that is just e to the x, so this will turn into minus e to the x, and why don't we multiply out this also, so this is e to the x plus x e to the x, and we see that some things cancel. There's our e to the x cancels with the e to the negative e to the x over here, and we've just got x e to the x. Now before we go on, there's one really important thing we need to do, and that is add our constant at the end, plus c, plus our constant. Alright, so now we've got an equation relating x and y, we've got our constant, we're ready to solve it. So let's go ahead and do that. Let's box this off so we don't get confused by it at all. And let's go ahead and copy this equation over so we can start solving it. Sine of y cubed equals x e to the x plus a constant c. So we want to solve for y here. So how are we going to get rid of the sine? Well, we can just take inverse sine, arc sine. So y cubed equals arc sine of x e to the x plus a constant c. And then how do we get rid of the cubed? Well, we just take the cube root. So y equals cube root of that expression, arc sine of x e to the x plus c. And there we go. That's our final answer. That's our final result. Now, in closing, there are also two things that I want to mention. First, in both of our examples, we were able to explicitly solve for y. We had an equation of x and y, and we were able to solve for y as an explicit function of x. But this isn't always the case. Sometimes we can get an equation which we can't solve explicitly for y. So if you ever find yourself in a situation where you separate and you integrate, and then you find yourself in a situation where you just cannot figure out how to solve for y, don't worry too much, because the equation might not actually be able to be solved explicitly for y. That might be the best you can do. The second thing is that in both of these examples, we focused on finding the general solution to the differential equation, which meant we had a constant and we carried that all throughout our computations and ended up with the constant at the end, representing infinitely many possible solutions to the differential equation. But when we apply differential equations to real-world problems, we're usually interested in a specific solution, which passes through a particular point. In the future, we'll learn how to choose that constant so that we can find the specific solution we're interested in.